I'm going to look at a question that is about alkenes. So the question starts off testing our knowledge of the reactions of alkenes. So we've got to complete the flow chart by adding the structures of the organic products of the reaction of this alkene here with hydrogen in the presence of a nickel catalyst, bromine and HBr. And notice that there are two boxes here because there are two possible products. And then the next part of the question, we have to complete the reaction mechanism for the electrophilic addition reaction of methyl propene with bromine. And don't forget your dipoles. Next part of the question, we have to calculate the molecular formula for cyclohexene. That's this one here. And then we have to do a percentage yield calculation. Definition of atom economy, and then we're then told there's another way of preparing cyclohexene, so this reaction here, and we have to comment on the atom economy of this method compared to that in C. I'll just quickly go back to C, so we're comparing it with this method here. So if you'd like to have a go at that, and then I'll go through the answers. So the products of the reactions, just remember when alkenes react, the carbon-carbon double bond breaks and the molecule that's adding adds across the bond. So essentially you put one part on this carbon and one part on the other carbon. So there's the product for hydrogen and nickel reacting with this alkene. There's your product for bromine, and when it's HBr, the H can add there and the Br can add there, which gives you this one, or you can do it the other way around, Br here, H here, so you get this one. The mechanism, so relevant dipole, the carbon-carbon double bond, high electron density, repels the pair of electrons in this covalent bond towards this bromine, so the dipole's this way around. Pair of electrons from the pi bond in the double bond will come out to this bromine. That will repel this pair of electrons completely onto this bromine and effectively break that bond by heterolytic fission. And the carbocation intermediate that's formed would look like this. And the bromine, because it's effectively gained an electron, it's gained the electron in the covalent bond that was belonging to this bromine, is in the form of Br minus. So you can show that as a lone pair. There's the new pair of electrons it's got. Don't forget the negative charge. And the curly arrow must start from the lone pair if you show it to the positive carbon, or you could take it from the minus sign to the positive charge. Part C, we've got to work out the molecular formula for cyclohexene. So it's this molecule here. We've got 6 carbons, and on each of these carbons here that have the single bonds between them, we've got 2 hydrogens. On these 2 carbons, we've only got 1. So that comes out at C6H10. The percentage yield, so we're told that 7.65 grams of cyclohexanol is reacted and the student obtained 0.0268 moles of cyclohexene. So the first thing we need to do is work out how many moles of cyclohexanol the student used. So that's 7.65 divided by the MR, which got you a mark, which is 100. So the students used 0.0765 moles of cyclohexanol. The 1-to-1 ratio in the equation would say that the theoretical yields of cyclohexene should be the same but that's all they got. So as a percentage, it's the actual over theoretical multiplied by 100, and there's the answer there, 35%. The definition of the term atom economy, it's the MR of the desired product divided by the MR of all the products multiplied by 100. And then we had to comment on this method here compared to method C, and you can see in this process here we've got an atom economy of 100% because all of the atoms in the reactants go to make the product. There's no other product, no waste product, whereas in C you can see that there's a waste product of water. So two of the hydrogens in this and the oxygen actually don't go and to make the product, the desired product. And that's the end of the question.